And when you use that mass and that measured gravitational force, you get 9.8 newtons per kilogram when you put them into the formula. And I'm not going to go through all of these. This was from Friday. We always get 9.8. And if you do it more accurately, you get 9.81. Okay? But now I'm leading up to the new part. And this is really important. When I say it's really important here, I mean it's important and it's also difficult to follow. It's complicated. That if you talk about the gravitational field of the Earth, so this is the Earth. When you talk about the gravitational field of the Earth, it exists because of the mass of the Earth. And the gravitational field of the Earth at this point exists because of that distance. And without reliving the entire lesson from Friday, we said the gravitational field will depend on the mass of the source and the distance from the source. We said that about all fields, didn't we? The strength of a heat field depends on how big the heat source is and how close you are to it. The strength of a sound field depends on the volume of the speaker and how close I am to it. So I want to make a note here, and I want you to make a note, that this big M in my picture is not the mass that this alien is hanging from a spring scale. This big M is the mass of the Earth. So listen very carefully. This is an experimental way to find the gravitational field of the Earth, but it makes no reference to these two things that we said the gravitational field depends on. In other words, the gravitational field of the Earth should be calculable. We should be able to calculate it without referring to test objects and spring scales. There should be a way to determine it from the mass of the Earth and the radius of the Earth. And this is kind of where we left off. So, warm up. Consider a test mass in a gravitational field of the Earth, and the gravitational influence is a gravitational force on it due to the gravitational field. So we've got a number of things going on here. This, I'm just going to write this a little bit bigger. This is the test mass that's placed in the field, and it experiences a gravitational force. You're with me? All right. This is the mass of the source of the field. And this is R that determines the field. So on the one hand, we have this, which can be used to calculate the gravitational field strength. But that mass that I've highlighted and that gravitational force that I've highlighted are not about the source. Let me ask you a question here. If I were like Doctor Who and I could snap my fingers and make this satellite disappear, so there's no more test mass and there's no more gravitational force on it, is there still a gravitational field at that point in space? Yes. What determines the strength of the field? What determines the strength of the field is what I'm going to highlight in green. The mass of the source of the field and R that determines the field are what are determining the field. So, what are we asked? Write an expression for the gravitational field strength of the Earth at the place where the satellite is. Well, it's the gravitational force over the test mass. And that's basically where we ended on Friday. We didn't get this far in the lesson, but we ended on Friday by saying this is how you can calculate the gravitational field. Okay. this was Marvin the Martian's experiment, except he did it on the surface of the Earth. Now, use Newton's universal law of gravitation to show that the expression written in A can be equated to another expression that has the mass of the Earth and the distance. Well, the force due to gravity between the satellite and the Earth is G times the test mass times the source mass over r squared. Would you agree? I want everybody to get an answer to this question in your head. What is the test mass in this warm-up? What is the source mass in this warm-up? Alex, what's the test mass? The satellite mass. What's the source mass? The Earth. And we've said that G is the gravitational force on the satellite, on the test mass, over the mass. That's equal to G. But if I just take this equation and I divide both sides by the test mass to get this expression, what would I have left? I would have G, capital G, times the mass of the source over the distance squared. And again, this is a higher level thinking. The concept of a gravitational field is very abstract. But if this is G and this is equal to G times the mass of the source over r squared, then this is G as well. So try to follow along with this, and when I say that, it's because even as I'm formulating in my head what I'm about to say, it's complicated for me. So I'm asking you to think carefully about this. If putting a random test mass in a gravitational field and measuring the gravitational force allows you to calculate the gravitational field, but that happens to be equal to G times m of the source over r squared, then this is a way to calculate the gravitational field as well. And what I've highlighted in green contains the things that should determine the strength of the field. Source, distance. So we actually have two formulas here. You have gravitational field strength equals force on a test mass over the test mass, and gravitational field equals capital G times the mass of the source over r squared. So if we read what I've got on the screen here, this second equation makes more sense as it defines gravitational field in terms of the source of the field and how close to the source you are. This gravitational field exists even if I rub this out, right? The gravitational field does exist there at that point in space, whether there's a satellite there or not. So how do we calculate it? Using that. So we're going to go through a couple of examples today, and then we're going to have some practice with this. You guys don't currently have an assignment, do you? The pulley thing. I said I would take it tomorrow, did I not? So you might still want to polish that up. I don't know. How many of you are done? Okay, so that's good. You got something to work on. We've got these two formulas. Take a look at your formula sheet, please. Make sure you know where they are. I'm really, everybody, not a fan of the second formula. I think you need absolute value signs around it. It may not be a big deal in Physics 20, but when we get to Physics 30, there's going to be something about it that will necessitate us having those absolute value signs there. So you might as well get used to it now. One A, find the gravitational field strength on the surface of a planet whose mass is that and whose radius is that. So if you take a look at this situation, you have a planet. Planets are mostly circular, basically circular. This is the radius, and the mass is given to you. If I want to find the gravitational field strength of the planet at that location, I could get on a rocket and go to the planet and hang this from a spring scale, measure the force, measure the mass, and divide them. Or, since I know the properties of the source, I can use this formula. So little g is 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared times the mass of the planet. Divided by, so everybody, we're dividing by the distance from the point of interest to the center of the source. But when you're on a surface of the planet, that distance is the radius of the planet. If I said to you, what is the gravitational field strength at this point here, then you would have to use that as the distance. Okay, so we want to be careful about that. But it's on the surface of the planet, so we can simply put in 2.50 multiplied by 10 to the 6 meters per second, or meters quantity squared. When I hand back your quiz, some of you may have a comment there. You need those brackets. If you do this, it's a minor quibble. It doesn't interfere in your ability to get right answers. But if you do this, what you're really telling me is you're squaring the meters. You're telling me it's a number of square meters. So you do need a set of brackets around there. Everybody give this a roll through your calculator and see what kind of number we get. You got it already, Nate? What do you got? 485.56. Well, that could be. I don't remember. Is that right?
485? Yeah.
Wow. You want to be walking around on that planet. I'll talk about what that means in a second. So let's round to the nearest whole number. Would it be 485 or 486, Nate? 486. Does everybody else get 486? Okay. In the next unit, and I think you know me, I don't like to just go, okay, well, that's the answer. This is newtons per kilogram. I don't like to just say, well, that's the answer, let's move on. Let's talk about that a bit. In the next unit, we're going to talk about G forces. How many of you have heard of G forces? So when a test pilot is training for NASA, they might be subjected to 6 Gs. And 1 G is what we're all experiencing right now. You walk around, you're carrying your own weight, you walk upstairs, you carry your weight up the stairs. If you were in a 2G environment, you would feel twice as heavy. So if I was walking around on a planet that was 2 Gs, I would feel as though I was carrying my twin on my back, which I could do, but not for very long, right? And the number of Gs, I'm going to say the number of G forces, is going to always be equal to the value of G over 9.81, which is what we're used to. That's 1 G. So on Earth, we experience a G of 9.81 newtons per kilogram. If I take 486, and I'm just going to use 486 and not the decimal value, and I divide by 10, I'm just using 10 instead of 9.81 because it's a nice round number. I get 49 Gs. So what would that be like? It would be like me somehow carrying 48 identical masses on my back. And you can pack it down to a manageable size if you want. But needless to say, I would just be a smear of material on the surface of this planet. I wouldn't be able to move. My bones would be crushed. All of my organs would be flattened. So this would be an incredibly difficult environment to walk around on. Well, impossible. Okay? So the next question. What are two different interpretations of your answer? What does it mean for me to say that G, and I'm going to include a vector here, is 486 newtons, 486 newtons per kilogram toward the planet. Let's include a direction. Well, what it means is a 1 kilogram mass would weigh 486 newtons. That's one interpretation. Each kilogram of mass weighs, weight is a force of gravity, weighs 486 newtons. What's another, I don't know why I spelled each that way. What's another interpretation of that number? On Earth, would you agree that the equivalent statement would be each kilogram of mass on the surface of the Earth weighs 9.81 newtons? What else is important about that 9.81? It's the acceleration due to gravity. So another way to interpret this is the acceleration due to gravity is negative 486 meters per second squared. On the old formula sheet, and I wish they wouldn't have changed it, they had G equals, and they had absolute value signs, 9.81 newtons per kilogram. And then they also had this, and I like that because they're two. The number is the same, but they're two different ideas. One talks about the force compared to the mass. The other talks about the acceleration of an object if it were released. All right. Take a look at the next question. What is the weight of a 12 kilogram mass on the planet? In this unit, we learned that weight equals m times g. And Aoki, you and I remember having that conversation about, we don't worry about the direction when we talk about weight. We don't need to say the weight is down. Well, that would be 12 kilograms times 486 newtons. And again, if this were an exam question, we might want to be carrying more decimals, but I'm not interested in that. 5,832 newtons. This is a difficult thing for us to wrap our heads around because we don't think of newtons. We don't think in terms of newtons, do we? I mean, if I told you something weighed 5,832 newtons, you have no idea of what we're talking about here, right? So let's compare it. This is on planet X. I don't know what the planet is. It just said some planet, right? What about on Earth? What would the weight, this is nice because it goes back to what we talked about with weight. Weight changes depending on the gravitational field it's in. Mass doesn't change. So on Earth, this would be 12 kilograms times 9.81 newtons per kilogram. And I made a mistake here over here. This should be newtons per kilogram. (118 newtons). So, what's something that is 12 kilograms? Let's see. 12 kilograms is about 30 pounds. And you can get them in 12 kilogram ones, right? So it's a pretty heavy weight, right? It's about 30 pounds, I would say. Those water jugs, those 5-gallon water jugs, that's 45 pounds, which is about 18 kilograms. So it's in the right neighborhood. And if you take those dumbbells or a couple of those water balls and you hold them one in each hand, that's a fairly heavy weight to carry around, right? So how many times more is 5832? Well, it's going to be that same number we got before. 5832 divided by that. Now, it'll be a little bit different, but about 49.5, 50 times as heavy. So imagine trying to carry 50 of those. So you just couldn't do it. When we take a look at this last question, if you could throw this object up at 20 meters per second, how long would it be in the air? Now, I hope you understand it's not going to be in the air very long, because the acceleration due to gravity downward is so large. Let's use VI equals positive 20 and VF equals 0 and find out how long it's going to take for that object to get to the top of its flight, and then we can double it. We do know that A is negative, I've forgotten that number already, but was it 486, Nate? Okay. Negative 486 meters per second squared. I guess we can use A equals VF minus VI over T. Now that you have all had more experience with physics and kinematics, I hope you're okay with me not including vector symbols here. We know the directions are important. I'm just not writing them. VF is 0, so we end up with A equals negative VI over T. I'll have negative 486 equals negative 20 over T. I'm going to have to take the negative 20 divided by the negative 486. Or 20 divided by 486. The negatives would cancel. 0.041 seconds. That's how long it would take for the object to reach its maximum height. If I want to find the total time in the air, I can double it. I missed a 0 there. Thank you, Alex. Maybe to give you a visual kind of spatial idea of what's going on here. It would rise to a height. Wrap your head around this. If it left my hand here, it would rise to a height of 0.4 meters above it. I'm actually surprised it's that big. But it's going to go from this hand to this hand and back in 4/100ths of a second. Like that. I mean, you wouldn't even see it. It'd just be a blur. And again, this all presupposes that you could actually physically throw the object up at 20 meters per second, and you can't. Okay? All right, that's it. The biggest thing I can tell you here about gravitational field strength is summarized with this. And I don't have vector symbols here or absolute value signs, but the formula on the left is used whenever you have a test object you're putting in a gravitational field. And the formula on the right is found or is used whenever you're just talking about the gravitational field knowing the properties of the test object. I hope that is clear. I feel a little bit off this morning, but what you are working on for the rest of the class, you got lots of time here. The assignment, all of the problems attached to that. You have about 45 minutes here, plus the pulley assignment, which is due at the beginning of tomorrow's class. Pitter patter.